So good morning, everyone. It's a pleasure to be here at this conference to give the keynote. So my name is Gurdip Singh. I'm the division director for the Computer and Network Systems division in the SAIS Directorate at NSF. I wear two hats. So I'm also the divisional dean here for the School of Computing at George Mason University. And so although I have two hats, I'm only allowed to wear one hat at a time as per the federal rules. So today I'm going to be wearing my NSF hat and talking about that. So basically, supposed to stick to NSF topics and not my personal views. So this talk is going to be, focusing on the programs and all that we have at NSF in the general area of computer systems, cloud computing, and others. All right? So again, thank you all for coming for this conference, both in-person attendees and those who have joined virtually. Things are opening up, so it's very great to meet everyone in person, and it's just a pleasure seeing everyone. All right, so just to sort of give a little background, so NSF, is okay, so I think this is. So should I stop share and just share this screen?
Okay, I stop sharing here, and
then let me just see. So is it
yeah, and we can choose which window we want.
this one?
Okay.
Yeah, that way, then there will
Yeah.
No, okay, let's finish this.
Oh, we can. I think that part will disappear of a minute.
Okay.
And
So no, this is good.
Okay.
Okay. All right. Thank you. So now everybody can see all of it. So NSF and in particular SAIS, we do focus on all aspects of the research pipeline, both from foundational, translational, and also looking at societal impacts. So in that sense, if you're looking at foundational research, so SAIS has funded research that has led to fundamental research in how information is gathered, analyzed, and communicated. So, all of the recent big news that you have seen in terms of black hole discovery, and also SAIS researchers played a very, very foundational role in this. We also look at translational research, which is basically taking the foundational research that we have and transitioning it to into companies. So we have had quite a bit of economic impact of SAIS related research that we have. And then finally, we are also looking at societal impact. So trying to sort of see places where industries have not yet seen a business case for going there, but we do want to sort of have our research, our cutting edge research, not only just informed by societal problem, but also impact the societies directly. So we've been trying to look at how we can use the research that we have and benefit the communities. So again, we've a lot of activities in that way. So just to sort of give you a brief overview of SAIS organization and core programs. So NSF is organized into several directorates. So there are, 8 directorates, which are spanning all of the areas of science and engineering. The very new one is the directorate for translational, so technology, innovation, and partnership TIP. And that's sort of looking at how we transition some of our research into practice. So within the SAIS, which is the Computer and Information Science Engineering Directorate, which funds all of the computing-related disciplines. So that is organized into 4 units. So we have our SAIS leadership. Margaret Martineau, she is our is our assistant director leading the directorate, and Gurdip is our deputy assistant director. But we have these four units in there: Office of Advanced Cyber Infrastructure, Computer and Communications Foundation, Information Intelligence System, and Computer and Network Systems. Each one of these divisions basically have what we call the core programs that fund, the areas within that. Just to sort of give you sort of the overall budget. So just as a pointer to give you the scope, the size budget, NSF budget was about 8.8 billion. And of that size budget was around 1 billion. FY23 budget, there is an increase that has been proposed, and we will see where things land. Okay. We've also, recently heard about the Chips and Science Act. So that has a lot of implications for science funding. And in particular, there is, money that has been authorized but not yet appropriated for NSF for research, not just related to semiconductor but all other areas. So we'll see, where things stand when the federal budget comes to pass. Size by the numbers. So these are FY21 numbers. FY22 numbers are not yet finalized. And so, as I said, we have roughly about $1 billion budget in computer science. Received about close to 7,000 or so proposals that were evaluated. 1,700 were funded. So funding rate is about 24%. But the important thing is to also look at how many institutions have been impacted. So we've supported about 373 distinct universities. So that's quite a bit of reach that NSF has in terms of funding computer science research. About 6,000 graduate students, 19,000 overall, all states that have been impacted. But more importantly, right now, we are also focusing on minority serving institutions. So 73 of these 373 have been those which are minority serving institutions. So we are trying to reach them as much as possible. So this sort of gives you, just a slide which gives you the overall initiatives. As I said, each one of the units, divisions have their what they call the core program. So for example, Computer Network System looks at networking research. IIS looks at AI and data science and all of that related research. CCF looks at software engineering, programming languages, quantum, and all of those research. But then we also have what we call size-wide initiatives. So these are programs that may cut across disciplines. And so we have a number of those. And then we also have NSF-wide areas. So these are not just within computer science, but we also want to partner with other disciplines. So we have multi-directorate initiatives, and many of those, are led by SAIS, and some of those have been listed over here. Some of the overarching themes over the past year or so that we've been focusing on, saying, we've been funding research for a while, and we have, all of the topical areas covered. But what are the new things that are kind of that are emerging and sort of helping us drive the research agenda? So the first one is, it's the, there is right now we are reaching the end of Moore's law and our scaling, where where a lot of the advances basically came out of how do you sort of pack more transistors into into the chip, and increasing the computing power. So a lot of the advances were sort of coming from that. And now we are kind of reaching the point where that no longer holds. So this is a point where we have to sort of see, if there have to be more advances need to be made, there has, more advances to be made, how do we go about doing that? So this sort of impacts all aspects of computing, hardware, software, security, reliability. It's new ways of saying where is the next innovations, where are the next improvements that are going to come. And so this size in the post-Moore law world is sort of providing a seismic shift, and we are trying to sort of look at, encourage the community to think more innovatively, more broadly in terms of how to go about it. The second thing that's sort of on is on everybody's mind is the transcendence of AI. So AI is there now everywhere, right? And so we basically not only have foundational AI research to look at, but we also sort of looking at how AI can help in other kinds of research, whether it's AI for improving networks, and maybe then, but then also conversely, how networks can support better AI. So there is a lot of activity, a lot of research programs that are being shaped around, how AI is kind of permeating all of the different fields, not just in computer science, but everywhere else. And how do we sort of do more innovative research in there? And the third one is what we call designing beneficial socio-technical systems. So again, these are, one thing pandemic has taught us is that, it's, how we came out of pandemics. There were two things, one is healthcare was one of them, but it's also that everybody was working from home. Everybody was, all of the, so it's the networking infrastructure. It's all of those kinds of things that really brought us out, held the economy together, held the country, whole world together in terms of operating smoothly and coming out of that. So that's an example of a socio-technical system that computer science research has been funding, and we have been doing research on that. So all of the research that we have done prior in terms of networking and cloud and all of those sort of came to bear and helped us there. So that's kind of an example where we are trying to sort of say that these systems, computer systems, these are socio-technical systems. These are not just technical, but they are also sort of have societal implications, and how do we sort of move forward? So if we sort of look at, the overall, the kind of things that are of interest to us, we, again, apart from the core programs, all of the new initiatives, we have kind of, put them into these buckets there where things are looking at post-Moore seismic shift, AI for everyone, designing beneficial socio-technical systems. I talked about these. But then there are, other pillars that the current administration and all of those are talking about quite a bit, which is climate and sustainability. So that's, again, top of our mind in terms of how do we sort of use computing to address them. And the third final pillar that we are looking at is equity and broadening participation. So that's also, again, administration's priority. And we are looking at, how do we sort of make computing accessible to everyone. So not just computing education, but all of our systems, computing systems, whether you call it broadband technologies, everything, how do we make it accessible to everyone? But then we also want it from the researcher viewpoint. How do we fold in researchers from many different backgrounds, many different into the mix there? So how do we encourage all of that? So number of our programs that we have are being designed on that particular pillar, and how do we sort of bring equity and broadening participation in both computing education and computing research. So what I'm going to now talk about in the rest of the talk is sort of focused more on the topical areas of interest to computer and network systems division, the division I belong to, and really want to sort of talk about, what's our vision around the research agenda that we are shaping in that particular division. So really, it's sort of focused about what's the next generation systems going to look like. Okay. So if you look at, services that we have, networking services, IoT services, apps on your phones, whatever it is, what things that you. Now, it's more and more that people are expecting these services to be very much like utilities. So you go to a home, you develop a new neighborhood, you know that there is going to be water, there is going to be electricity, there is going to be roads over there. So similar to that, they are going to expect all of the other services, networking services, IoT services are going to be available. You just turn the switch on, and those services are going to be available over there. So it's not just there for housing and but also businesses, offices, everywhere. You want to be able to just have these things just by the flip of a switch, and you want to be treating them very similarly. Water service, very reliable. You turn on a tap, water will be there, heating will be there, electricity will be there. And we want these also, the IoT internet services, to be the same way, that these need to be there, reliable. So what are the characteristics that we are looking at? So really what the next generation systems are going to be, that, it's going to be really at the convergence of connectivity, compute, and control. So we've been looking at many of these things separately, but the next generation systems are going to look at all of these converging into these systems. Every system that we are going to look like will have computing, connectivity, and control aspects to it. So some of the elements there is that, challenges that we are going to face. Again, we've been funding research on this for a while. One of the things that's going to be there in the next generation system is the densification. There's going to be more and more and more of these IoT devices and all of the other, services they're being deployed. In a room like this, you can expect hundreds of devices being there, each one of you carrying several of them, and then there are the room itself being, outfitted with many, many devices. Even now there are so many, but you can expect 10 times as much densification. So what this means is that, again, is that the system that you will need to be designed need to be scalable. The architecture needs to be scalable. If you're looking from whatever aspects you're looking at, if you're looking at from connectivity viewpoint, you need to be able to provide 10 times as much bandwidth that's there. It needs to be scalable in terms of wherever your computing architecture over here, the computing needs that you have needs to be scalable over there. The control aspect also needs to be scalable. So scalability is going to be a very important thing in the next generation. Whatever we design need to be very, very scalable. The other thing is going to be that there's not going to be, there's going to be disaggregation and distribution. There's going to be no centralized control. Things are going to be more distributed. It's not going to be your traditional, for example, the cloud system where everything happens centrally in a cloud. It's going to be a lot more distributed. It's going to be computing happening at the edges. It's going to be continuing from edge to cloud. So these architecture, the next generation systems need to have all of these computation, connectivity, control to be distributed. And it needs to be localized. So it needs to be, there's no central control. It needs to be distributed control. So those are, another aspect that the next generation systems will have. There's also going to be a lot of heterogeneity. Okay, so all of these devices are going to be very different, different types of devices from many different vendors, network technologies, again, from different vendors, middleware applications. So there's going to be a very, very diverse set of resources that are going to be available in your underlying infrastructure there. And you will then have to develop these end-to-end applications, compose them, develop them, and be able to deliver end-to-end services. So we'll have to deal with this heterogeneity, various ways to deal with. There needs to be standardization, standards need to be developed. That's one way to look at it. But again, there needs to be a lot more research on the formal methods, proper interfaces. If you need to dynamically put together things, they need to talk to each other. The interfaces need to be very well defined. You need to see how the properties of these systems that you configure end-to-end with end-to-end services how are they sort of leveraging the properties of the individual components and delivering an end-to-end service over there. So there is, a lot of work to be done on defining proper interfaces, defining how these large-scale systems compose and behave in a predictable manner. Among the properties, again, as I said, one of the things that with the IoT services or other utilities is that, they are available at any time. So similarly, our IoT services need to be available anytime, anywhere, without disruption. That's the expectation, which means that, you need to look at planned scenarios. There are certain plans scenarios that you can predict, failures, disconnected operations, remote locations, but then there are going to be unplanned scenarios as well. So unknown environments, extreme environments, and your system needs to be designed in such a manner that they are resilient to these different types of scenarios, and they provide services at any time, anywhere. They need to be trusted services. That means need to be secure. That's a very important thing. Need to be verifiable, high assurance. Again, depending upon the type of service. So some of them may require more, it might be more time critical. Some of them may be safety critical. Some of them may be, more dependent upon privacy and all those things. So all of these properties need to be addressed in the next generation system. Quality of experience is also going to be very important. So again, if you're looking at your services, for instance, AR, VR services, and also the type of experience people have is going to drive whether or not that particular application is. So these are, many of the things that are sort of driving what our next generation systems are going to look like. So how do we sort of fund research or develop a research agenda regarding these systems which are driving this? So again, we've been funding research on this quite a bit. And so I'm going to talk a little bit about the programs that we have already have, which address many of these aspects. And then talk about some new programs that we are developing, which are addressing some critical gaps in these. So the first one is a networking systems research program. And again, this program has been, funding networking research for quite some time. Over the past 3 to 4 decades, we've been funding broad research in the area of networking, and this is the program which has pioneered research through the years on different types of whether you're looking at 2G, 3G, 4G networks, 5G networks. We've been sort of on the wireless side, on the wired side also, looking at scalable internet architecture. So these research has been funded by the NETS program for quite some time. So NETS, again, overall, it seeks to advance fundamental research in both wired as well as wireless networks, and we are, it's looking at, high performance, robust, manageable networks. And I've listed some of the topics that this research has been traditional. So again, moving forward, if you are looking at, next generation networks, so some of the topics that this particular program looking at is, in the near term, we are looking at, again, how looking at software-defined systems, looking at AI, 6G and beyond. In the midterms, there are, a number of things, again, trying to sort of expand that particular boundary of networks. And in the, long term, we are looking at, how we can look at quantum networks. So we do have some proposals that we are funded right now on quantum networking, optical networking, looking at terahertz networking, and, different types of domain-specific networks over there. So that's kind of what the networking program, again, looking at next generation systems from the networking viewpoint. You can also look at it from the computer systems viewpoint, where you're looking at it from the computational side. How do you compute given a particular networking architecture is available? So that's the computer systems research. It's basically looking at computer research across the layers horizontally, vertically, and also horizontally as we sort of expand it from a single computer system to multiprocessor systems, to your local area net systems, to grids, to edge, and to IoT. So this is looking at, how do you develop computational architectures, computing architecture across these things. So, traditionally this research has funded, going back 20 years, it was operating systems research and all of that, but now we are looking at middleware and the entire protocol, entire stack over there. And then again, as I said, it's looking at horizontally across on the distribution axis. So some of the areas that this particular program addresses is on, edge cloud computing, real-time system, variable technologies, runtime systems, and so on. So this is again looking at from the computational view. Once you have, that, you also need to look at it from the security viewpoint, and that's the Secure and Trustworthy Cyberspace program. So this program again was launched in 2011. It's looking at it as a socio-technical problem. It's looking at it from this multidisciplinary perspective, where it's saying security is not just a technical problem. You need to look at it from societal viewpoint, how people react to security, are the usable security. And so we do sort of, this program is looking at research at the intersection of computer science, engineering, and social sciences. Okay, and we sort of invite proposals in all of those domains. So again, as we look at, the next generation systems over here, this secure and trustworthiness is going to become more and more important. So, data is kind of central to next generation systems, and ensuring data privacy and its use is going to be very important. So people are talking about the concept of data economy, where you can, use data. The idea is that how you can have data that you can monetize, share, and monetize that. But in order to do that, you need to have these architectures there, which allows you to do the computing or allow this data to be shared and distributed and computed upon in a confidential manner. So the area of confidential computing, which sort of allows, it's kind of a platform which allows you to set up rules on how you want your data to be computed upon, how you want it to be shared in a very, very user configurable manner. So that's kind of a new avenue in the SATC domain that we are looking at, which is going to be very relevant to the next generation systems. So cyber physical systems is perhaps one of the very first programs which sort of looked at next generation systems in a comprehensive way. So this was a slide that was, or a graphics that was designed in 2009, where we looked at, cyber physical systems as with intelligent highways, intelligent waterways, smart buildings, smart airspace, and on and so forth. So the cyber physical systems world sort of imagined that there are going to be these types of systems. These were next generation systems at that point, and all of these sort of involved interaction between the cyberspace, cyber, and the physical. So it's not just cyber alone, but you are looking at cyber and the physical and the interaction between them. So the cyber physical systems program sort of looked at it from that point of computation, control, and sensing in an interactive manner. It looked at networks at multiple scales, and from small scale networks, your control and all happening within a car, to very large networks like your intelligent highway, and how do you sort of do communication control at that particular scale. So when looked at, in many, many different areas and domains, this is kind of the graphics that we use for the cyber physical systems program, where the petals of this are sort of describing the areas that it has impacted. And the core is the one which is where, you are doing research, which is at the intersection of computing and control. So cyber physical systems program is again one program which is again gearing up for the next generation systems, where we are looking at the past 10 years or so in the cyber physical systems research. We have made considerable advances, but our models again are not at the scale that we want. So we are able to do, self-driving cars are reality. We have been able to do control at that particular scale. If you look at, your medical wearable devices, we are able to do control on that in that particular space. But now, if you look at scalability issues over there, how do you scale to very large cyber physical systems? How do you develop models of those systems? Because many of these things need to be high assurance and verifiable. So developing large-scale models of these large-scale systems, scaling up those techniques is kind of the next frontier for the cyber physical systems. Quickly, I want to talk about Smart and Connected Communities program. So this is another program which looks at the research that we have been doing in this, and then transitions it into the communities where there is a real need. So this Smart and Connected Communities program again is taking much of the research that we have done in cyber physical systems, networking research, security research, and then applying it to address societal problems. So it's looking at use-inspired, community-focused research. So it's requires partnership with communities, looking at a problem which the community is facing, and trying to see, can we solve it now? If we cannot solve it now, what research needs to be done? So that's use-inspired research. You're looking at specific problems, trying to address it, and then developing a research agenda. So Smart and Connected Communities program has been around for now about 5 years or so, and it has gathered considerable attention. As an offshoot of that, we have also developed another Civic Innovation Challenge program, which in the Smart and Connected Communities program, it was the academics which were taking the initiative, going to the communities and saying, tell us what problems need to be solved. In the Civic Innovation Challenge, we flip the dynamics. We are saying the communities need to take the lead and identify a problem, and then approach academia and say, hey, here is a problem to be solved. Concrete problem, we give them a year to solve this problem. So these awards are 1 year, $1 million, solve the problem. So this has been, very successful. In the first stage, we had 2 types of problems that we wanted to address: communities and mobility, basically trying to see how do you sort of provide mobility solutions from where people live to where they work. And that's a perennial problem in many, many communities. And that sort of discourages people from taking up jobs because these solutions are not there. So that was one particular track that we've done. And the second one was resilience to natural disasters. So again, this has garnered quite a bit of activity. This sort of tells you so we've made 17 awards in stage 1, and we are now in the second round, where we are trying to have that computation. During that, 17 awards, this tells you the communities that have been involved. And there's been, as I said, a lot of outcomes from this. For example, we gave a grant to Wisconsin, Milwaukee to look at, again, this mobility options. And in a year, it was successful, and the city came in and put in 4.2 million. And we have 2 or 3 other examples where our project has now resulted in the local communities sort of trying to scale it up and implement it. So again, this is a kind of an example of a place where, we are taking research. Perhaps it was done 5 years, 10 years from now, but it's actually delivering solutions. So as we look to next generation networks, yeah, they may not be immediately applicable to our communities, but we are hoping 5 years from now and all they are going to have considerable. So this was kind of, the programs quickly that we already have and are sort of looking at how to tackle next generation systems. Now I want to sort of go over the new programs that we had designed. So as I said, when we were looking at next generation systems and we are looking at how to sort of develop the research agenda, where are the gaps? So two things that we found is, or the approach that we try to follow is that one is around partnerships. So we said NSF alone cannot do it. It needs to be a partnership because we just look at it from one particular perspective, but other stakeholders are looking at it from different perspectives. So we need to look at other agencies and we need to look at industry. All of these need to sort of shape the agenda for where the next generation systems need to look at. And the second, we need to emphasize somewhat on clean slate design. The thing is that if you give people an infrastructure and say, do research, they are going to do incremental research. If you give them 5G and say, here is 5G network infrastructure, they are going to then do security, for example, on that and develop techniques for that. They are not thinking innovatively out of the box. So we wanted to sort of say, how can we do clean slate design, give people the capabilities of doing clean slate design and developing these nets, saying that if you were to develop next generation system from scratch, how would you go about doing that? So that's been our focus. And so we've been designing, programs around that, research program, as well as infrastructure. Infrastructure is very important for people to experiment with. We need to give them infrastructure where they can do clean slate design. So if I want to design a new type of network architecture, they need to have place where they can do that, right? It should not be in simulators where I just do my own thing in a simulator, which cannot be replicated. You need to provide them actual physical hardware that they can use in order to do that. So one program that we designed, and there was the RINGS program, Resilient and Intelligent Next Generation Systems. So this was a program, as the graphics on the right-hand side sort of shows, it's a program in collaboration with NIST and DoD. But then there are 9 other industry partners that are involved. So you can see it's all the way from all the cloud companies, cloud to edge, and networking companies coming together. So we conferred with all of them and said, okay, let's try to design a program to address the gaps. And what we sort of said, okay, one of the things that we should figure out, again, we don't want to sort of look at the entire space. What's the most important thing? So everybody said resilience is the most important thing. So resilience, which means trying to provide the services anywhere, anytime. So we focused on resiliency as the main system and said, okay, we are going to get ask for proposals on resilient next generation systems. So again, when I talk next G, it is not just from the communication perspective, it's communication, computing, control perspective, all of these things together. It was a $40 million effort, and we've already made about 41 awards, $1 million awards on this. The graphics on the right, upper left-hand side basically shows the research vectors. So we basically said that you need to focus on some properties of resilience. You can do resilience through adaptability. You can do resilience by security, and you can show resilience by autonomy. And then you also look at, how do you want to show? What are the domain-specific aspects there? So maybe this is so. The one on the left, the green, is on the left-hand side, and group B is the enabling technology. So we said that you can pick how you want to show resilience, and then you have to say, where do you want to show resilience? You can do it at the networking level when you're looking at, your new radio approaches, spectrum utilization techniques. You can focus on edge to cloud. You can focus on applications, AR, VR, wherever. So you pick the vectors that you want, and you show your new resilience research in that. So it's kind of, again, trying to pick people from different disciplines. So they need to have a domain specific, someone who's a networking expert or an edge cloud expert or AR/VR expert, let's say focusing with an AI person who knows how to do autonomous reconfiguration of these, using AI to do autonomous reconfiguration and demonstrating some resilience concepts. So that's kind of what this program was designed on. So again, this program is on the way. It's, I believe, a great program, and that's how the RINGS 1.0 was designed. We are now sort of looking at, what's going to be the next. We have addressed resilience. What else do we want to do on the latest software? As I said, so again, we are designing research programs to address those gaps. The second important point I want to spend a little bit time on is, in the infrastructure. So I want to sort of give an overview of what are the infrastructure capabilities that we are providing in order to promote next generation research. This is a graphics of the various infrastructure program that SAIS supports. I know it's a number of them. We are trying to sort of design a better way of letting folks know what these programs are. And again, these are acronyms. I don't have the time to sort of go through, but let me go through some interesting ones. So this is a graphics overall of the cloud and network related infrastructure that we have. So we have a number of projects that we have funded across the country where we are providing different types of cloud resources and edge computing resources. And we are also providing a lot of networking infrastructure to interconnect all of these things together, and also to define new types of networks. So let me go through again. It's a busy slide, but the next few slides hopefully are going to show them better. So the first up is what we call the Cloud Bank project. So what this Cloud Bank project is, a very simplistic project. It's basically trying to provide services from the commercial cloud vendors. So we also wanted to bring the commercial cloud providers into the mix. So, Amazon, Google Cloud, and Microsoft Azure. So we have researchers and institutions who want to use it. So this is how sort of the Cloud Bank works. So we have funded an entity called Cloud Bank. It is hosted out of University of California, San Diego. Whenever you want to use some cloud, public cloud resources, and you're writing a proposal, you write a proposal to NSF and in that you indicate that you want to use some of these cloud providers. And once we make the award, that particular project is funded, we tell the Cloud Bank, which is the entity, saying, hey, this particular project needs so much of cloud credit. So let's say it's a $500,000 project and they've requested $15,000 worth of cloud credit. NSF will pay Cloud Bank $50,000 and say, set up an account. So account is set up, and you can tell at that time which particular cloud provider you want to use, and cloud account is set up, and you can do your cloud research over there. And then the usage for your cloud is then reported back to Cloud Bank, and Cloud Bank then pays the cloud providers. So this is a way in which we have designed a mechanism for Cloud Bank to be used, the clouds, public cloud providers to be able to got into the mix and be used over there. So I would highly encourage, people who have projects to sort of make use of this facility, both for research as well as education. Again, it's just quick recap of the status. It's now there in many different solicitations are eligible. We are on the average, we are getting about 15 or so requests per month, and it is scaling up. So we are seeing a lot of the usage of this Cloud Bank. We have also funded two major investments, which are NSF investments on cloud systems. One is Chameleon. It's based out of University of Chicago. And so this one basically, it's a test bed that we have funded. It gives you, you can adapt to your experimental needs. So again, the cloud service providers, the public cloud service providers like AWS and all just give you bare computational capabilities. These one give you bare metal access. You can actually configure and say, this is the type of system, bare metal system I want. This is the type of operating system, the images that need to be installed, and I want to do these kinds of experiments. So you can tailor-make a system based upon the type of research that you want to do. And you can do, again, it has also extensions for you to do edge to cloud experimentation. So you can attach your devices to this. Again, a lot of users for this. It's available free of charge to any academic researcher. So it's not just those who have NSF grants. Anybody can go and use this particular platform. Cloud Bank is another one, a very similar project that we have funded, another major investment out of University of Utah, and it has other locations at Wisconsin and Clemson. Again, build your own cloud using hardware resources, and being used quite a bit. So these are two, major cloud bank cloud projects that we have funded, which are available for usage to the public. Fabric is another project that we have funded. Again, those were the cloud projects, computational capabilities. Now we need something to network them. So Fabric is a project, it's a mid-scale project that we have funded, and it's a nationwide programmable network. And it has got significant compute and storage programming capabilities at each of these nodes. So you can see that it has these nodes where all of our other cloud investments are. So it's interconnecting those, and it's also providing these different places where in the network where things are all programmable. So again, it's part of the computing continuum in the sense that we see that computing needs to be done at the endpoints, but it permeates throughout the network over there. So it's programmable everywhere, and it provides you that capability of building a network from scratch, which has these programmable capabilities, as well as it has fairly very significant computational capabilities at the edges. We've also funded 4 projects which are advanced wireless research projects. We call them power test beds. And these are more on the wireless experimentation side. So this is about $100 million public-private partnership, and about 35 companies are contributing to this. Powder test bed at Salt Lake City, Utah. Again, it's a system that provides you to, again, build your wireless networks from ground up. So it provides you state-of-the-art facilities for computing, storage, communication, and so you can do innovative research in 5G radio access network architectures. They have spectrum available. You can look at different spectrum architectures, spectrum sharing architectures, and also, again, it sort of provides you can go on site and do this, but it also has a way in which you can interact with it remotely and do your experimentations. Cosmos is another platform. Again, this is more on the urban area where it's looking at ultra-wideband communication, low latency communication at the edges for these critical applications in an urban area. For example, one of the main test experiment is, a crossing in New York City where you need to look at pedestrian traffic, other traffic that is coming, and be able to provide, appropriate guidance to all of them. ERPA is in Raleigh, North Carolina. So this is the one which is sort of looking at unmanned systems. So they allow you, again, experiments of very different kinds, whether using your UAVs as hotspots and, networks which sort of look at these airborne assets as well as ground assets and provide network connectivity. And so you can experiment with innovative techniques over there. ERA is a platform which is looking at rural broadband. So how do you provide connectivity where in remote areas, rural areas, but then there may be needs, for example, precision agriculture and all, they actually have quite a bit of need in terms of not just real-time access, but also very high bandwidth access over there. So it's looking at that. So again, one of the things we are trying to do is to bring all of these are these power platforms, our fabric and the cloud investment together in a national infrastructure. So we are talking about, a national discovery cloud where there is all these different assets. We want to consolidate that into a single entry point. So as a researcher, I can go in and say, this is what I need. It can try to then determine what's the best resource for you to use. And this should be a single entry point. And it sort of gives you all of these different maps it you to the available resources. And as said, at the bottom layer, we have the different cloud services, the test beds that we have talked about. There is also a lot of infrastructure also available in terms of high performance computing that are some of the other offices are funding. So this National Discovery Cloud is something that we are going on. Our first step is towards National Discovery Cloud for climate change. So that's our first step that we are going to do, and then we are going to look at this concept overall for in general. Finally, just in the few minutes that I've left, also want to sort of mention two investments that we have made in AI institutes. So again, AI institutes, that's a very ambitious program that was launched to, look at our national competitiveness in the area of AI. So we have funded total of 18 AI institutes so far, but two of them are specifically in the area of computer systems. So one is what is called the AI Edge Institute, and its lead is at Ohio State University. It's basically looking at networks for AI and AI for networks. So how can we sort of look at, holistically develop networks which can support AI applications? But then how can we also use AI for networks? So again, it's sort of looking at, the networking plane at the bottom, where you have just different networks, different types of networks which are coming together. And then on superimposing on that, it's superimposing a distributed intelligence layer, an AI layer, which is embedded on top of them. And it is working together in terms of managing the network, but then also supporting AI. And this is, again, they are looking at 3 use cases, but the important thing over here is that, it's also, these different types of use cases, they are using all of our platforms that we have funded, whether it's our power platforms, fabric, and others. So this particular AI institute will be sort of bringing all of the concepts that we have talked about in this, all of the resources that we have provided together, and provided some leadership in terms of how these resources can be used to provide cutting edge research support to in this. Then other AI institute is Athena. This is led out of Duke University. Again, looking at AI and edge computing, very similar types of things. Here are the research thrusts. It's looking at AI-powered computer and edge systems. Same concept. How do we use AI to support the design better computing and edge systems? And again, how do we use these edge systems to support more AI applications? So whether those AI applications are at the edge and they are looking at functionality, efficiency, heterogeneity, trustworthiness. So overall, just to sort of conclude, as I said, we are looking towards, how do we go towards these next generation systems, which are going to have all of the requirements that we have talked about. We have a number of existing programs. We are sort of shaping them in order to address that. But at the same time, we are also looking at, rolling up new programs over here, which can move us towards that. So I guess time is up. So thank you and open for questions.